You want me to share my screen?
So yeah, uh, let me introduce you.
Okay,
Sagy is right, yeah? I pronounced it right, or Sagy is right? Sorry, I'm not good
Sagy.
at
Yeah,
Sagy.
you first, Sagy, yeah.
Okay, so, thank you. Dear participants, we're continuing now with the third amazing talk of Sagy Cohen, Associate Professor of the University of Alabama. And Sagy's primary scientific interest is modeling and analysis of hydrogeomorphic processes and dynamics in large global rivers. And he's also leading research and development efforts focusing on flood remote sensing, analysis, and modeling. You have about 45 minutes for your lecture, and then we have 15 more minutes for answering questions that would be written on YouTube, and I will transfer it to you.
Thank you.
So please start, Sagy.
Yeah, I'll share my screen. Let's see, where's my screen? Here it is. You see it all right?
Yeah, that's good.
All right. Well, first of all, I would like to thank the organizers and especially Sergey who invited me. This is one of the silver lining of the COVID pandemic, is to see all these initiatives pop up, which allow people from all over the world really to come together for free, basically, right? Or very, very cheaply. And I hope this is one of the things that is going to remain after we go back to normal, because I've been a part of some of these and even helped organize a few, and it's really great. So anyway, well done, and congratulations on a successful workshop. Today I want to talk about more general about recent advances and future direction in global fluvial sediment modeling. So this is a topic that I've been working on for quite a few years now. So I'm going to start with some introduction, which I like to put in terms of a question. So why should we care about fluvial sediment? And I'm sure the answer is clear to many of you, but nevertheless, I think it's good to spend a couple of minutes thinking about that. I'm then going to very quickly talk about some of the main mechanisms and drivers of fluvial sediment dynamics, at least that the one that are most related to my work at that scale. And finally, I'm going to talk about global fluvial sediment modeling, both a little bit about past or the evolution of that field, what we've been doing recently, and then looking at some future directions and very recent publication that came out by different people. I like to start my talks with this image that I generated in Google Earth. So Google Earth, I'm sure all of you, or most of you are familiar with it, allow you to basically patch together all these satellite images. And in this case, you see, I usually ask people, which river basin are we looking at? And some people can guess correctly, but because we don't have that interaction here, I'm going to tell you that this is the Amazon basin, looking from the outlet, from east to west in this oblique view. So the north would be this way. Oops, sorry. I was going to use my pen. Here we go. So this would be north here. So we see, the reason why I like to show this picture, first of all, it's kind of beautiful, I think, but it encompasses a lot of the processes and dynamics that I'm going to talk about. And if you know what to look for, you can actually see a lot of things just even from that really large scale image from space. And in the right corner, on the bottom right, you see an actual picture that was taken, I believe, from the International Space Station. And you can see the sediment plume. So this is the outlet over here. This is the delta. And you can see the sediment plume coming out of the Amazon River, and which you can't see looking at the Google Earth image, just because they mask the ocean. Anyway, so what can we see here in the Amazon? So we see quite clearly a lot of sediment, right? Even from space, we can see the sediment within the river system, which is quite amazing. Obviously, the biggest river in the world, but we can also see there's a lot of heterogeneity and a lot of dynamics here. So one thing that I like to highlight is the Rio Negro Basin here. You can see this black spot, this black line. This is the Rio Negro River, which has very little sediment load in it for different reasons, which I'm not going to go into. So already we see extreme sediment condition within this one big basin. We can also, if we know what to look for, we can see the source of much of the sediment in the Amazon basin, which is the Andes River mountain range that you can see sort of in the far distance, this brownish area, some white spots, which is snow. So a lot of the sediment that flows through the Amazon is coming from the upstream area, headwater area of the Andes mountain range. So it makes a long journey all the way to the coast. We also see the effect of humans on this basin very clearly, again, if we know what to look for, in the form of deforestation on land use change, right? You see all these areas all over, especially in the south part of the Amazon basin, a lot of land clearing. This is something that a lot of people have been looking at, and there's a lot of studies that have been done. It's a major concern. In the last couple of years, we've seen a lot of forest fires in the Amazon basin. Anyway, so what I'm trying to convey to you here is all these processes, all the way from the landscape, the hill slope, to the fluvial within the river system, and then finally at the coastal, what's going on once the river hit the ocean. So as I said, I like to frame my introduction in the form of a question. Why is fluvial sediment important? Why should we care, right, about all of that? And especially, why do we want to model that? So I like to split it into three domains or three environments: the landscape, the river, and the coastal / marine environment. So for the landscape, we just heard a talk about gullying, right? So generally speaking, we know that the process of sediment transport starts with the production of sediment or production of soil through weathering and so the pedogenesis, the process in which rock becomes soil, and then through soil erosion is delivered into the river system and is transported eventually to the coast or a big lake, or deposited on the floodplain. So the fluvial sediment component, which is in this diagram or this flow chart, is the last component, which is actually not really, but the fluvial part of that process is in itself indicative of what's going on at the hill slope upstream of it. So we can use the changes and characteristics of fluvial sediment to tell or to gain information about processes at the landscape, on the landscape, and at the floodplain. So at geological timescales, we can look, for example, at the deposition in floodplains to understand long-term processes and changes on the landscape. In more recent timescales, we can look at observations or modeling of fluvial fluxes to understand how changes, for example, in land use or climate change are reflected in sediment flux in rivers. In addition, the sediment itself is a major conduit of nutrient, carbon, and pollution. So there's a lot of direct impact or a lot of direct links between the sediment flux and what's going on in the aquatic environment, so ecological water uses and so on. Now, in terms of riverine, that's a more direct link, obviously, because we're talking about fluvial sediment, so obviously it has an effect on the river itself. So the morphology of the river itself is controlled to a large degree by the characteristics of sediment. So how much sediment we have, the particle size of the sediment, the flow regime, and so on. So a lot of it is controlled by the actual fluvial sediment. So just in terms of fluvial geomorphology, then understanding fluvial sediment flux is extremely important. In the field of aquatic ecology, then the functioning of a river system as an ecological environment also is directly linked to fluvial sediment, both in terms of bed morphology, so different type of or species of aquatic animal like fish, you know, and so on, dependent on very specific niches or bed morphology to reproduce, as an example. So understanding sediment within river system is very important for that. Also, the sediment load in river, or many aquatic species are very sensitive to very specific turbidity in the water and so on. There's also, river systems are major socioeconomic services, so transportation, recreation, fisheries, and so on. Water use, obviously, irrigation, drinking water. And sediment is a major factor in all of these. So we're going to talk a lot about dams in the rest of this talk. And then recreation also, again, related to a lot of other factors as well. And so there's not much to expand on this, but what I'm trying again to convey is why are we interested in fluvial sediment? So I showed you the Rio Negro and the Amazon and how different they are. So this is, I like to show this picture and I kind of zooming in. There's a city called Manaus in Brazil that you see over here, and it sits on the confluence of the Rio Negro and the Amazon. And so that extreme contrast between these two rivers and the confluence of them is actually became a major tourist attraction over the last decades. And people actually go on cruises to see that, that line between the Rio Negro water and the Amazon, which is very brown and heavy in sediment load. And it's such an extreme contrast that it's very cool. The temperature is very different as well. So the density of the water is different. Different aquatic animal can thrive in different parts. So this is all in the same location. You can sort of see it over here. And it's actually very interesting from many perspectives, including from fluvial geomorphology, because it takes a long time for the two rivers to actually fully mix. You can actually see, if you look closely, and I hope you can see that, but there's actually this line between them continue for dozens of kilometers downstream until it's fully mixed, because there's such contrasting body of waters. So just an example here, right, of geomorphology, socioeconomy, aquatic, all in one compact location. Okay, so I want to talk about, sorry, before I move on to the processes, I forgot this last bit, which is the coastal and marine environment. So again, the question is, why do we care about fluvial sediment? Because, and this is the third element, which is it has a major impact on the coast and the marine environment. And there's a lot of factors there. So obviously, the sediment characteristics of a river has a major impact of its coastal morphology in the, near its outlet. And some of the best examples of that are obviously river deltas, but that's also in places where you don't have developed deltas, then the beach geomorphology and the continental shelf are all responsive or in some sort of equilibrium with the sediment that comes out of their nearest river. Deltas are perhaps the most dynamic of those in many cases, because delta is basically the equilibrium or the results of the balance between the amount of sediment that comes out of the river and the energy that comes from the ocean, so that that these two processes are actually affecting each other very significantly. And the ecosystem, again, we always go to ecosystem. Ecosystem in the coastal environment are also very directly linked to marine environments. And that is because Sediment itself, as we said, brings a lot of nutrients. It affects water quality, both in terms of pollution and turbidity and so on. So marine ecosystem very much related to the amount of, or in the characteristics of fluvial sediment. And finally, socioeconomic, just like in river system, the socioeconomy of coastal areas are also can be greatly impacted by fluvial sediment. Actually, a couple of years ago, I spent a sabbatical at the University of Hawaii and learned a lot about the link between fluvial sediment and the marine environment. And there, it's a kind of a double whammy. First of all, they have the impact on coral reefs, which is not unique to Hawaii, but it's definitely a very significant process that raised a lot of concern with sedimentation of fluvial sediment that basically choke up or bury coral reefs. Recreation, as you can imagine, Hawaii is mostly related on tourism. And when you have very heavy sediment load, as you see in this picture at the bottom, they call it actually brown water day, and they close the beach in some beaches quite several times a year because of these heavy sediment loads that come to the beaches, and that has a significant economic impact on these islands. All right, the next topic I want to talk about very quickly, I'm sure many of you are aware of a lot of that, is the main mechanism and drivers that control fluvial sediment. And again, this is very, very quick and dirty overview. And again, not a lot of surprises there, right? But we need to, especially when we go into the modeling of this, there's several processes and drivers that we need to consider. The first being atmospheric, right? Because everything is driven by water. So the hydrological cycle, which is in our case starts with atmospheric processes, is key to everything. Without understanding and without representing a water cycle within our river system, then we don't have a chance of representing sediment. And therefore we need to know something at least about especially precipitation. At the hill slope scale, we want to know about soil production. We want to know about the movement or the initial movement of that soil through soil erosion. So these are the drivers that affect how much sediment and what is the characteristics of that sediment that goes into the hill slope. And finally, the fluvial itself. So the hydrology and hydraulic. So both the basin scale, sort of water cycle, as we said, or hydrology, but also the in-channel hydraulics, right? Because what's going on within the channel itself is actually very impactful in terms of sediment flux and deposition and bed load and all these other factors that I'm going to quickly talk about. The river morphology can affect fluvial sediment flux. And finally, flooding. We don't always, or not all of us always think about flooding constantly, but flooding or the extreme hydrological conditions are actually very, very important to the story of sediment flux, because flooding can be an extremely or exceptionally effective mechanism to move sediment and to change sediment and morphology dynamics. So flooding, a very difficult component or part of the hydrological cycle to model and to capture and to even to study and to observe, but very important for the fluctuation of sediment in the fluvial system. Now these pictures, this is a creek in near the University of Hawaii in Manoa, which is on the island of Oahu near Honolulu. And you can see Hawaii is a really great example of all of these processes, because much of the sediment, so at the bottom you see the river or this creek during normal times, which is very low water level, almost no sediment loading, even though this is a very steep creek. But then every couple of weeks you get this big storm come in, and there's all this water, all this soil erosion, and all that sediment, as you can see here, in flowing through that river system, that little creek. We can also see human impacts here. You see this excavator here. You see this banking, this armoring of the bank. It's hard to see the hill slope processes, but everything is all very much connected in a very small package, which is Hawaii. The last mechanism that I want to talk about is anthropogenic. I'm going to talk a lot about in terms of the different studies that we've been doing, but humans are a major force, as we all know, in terms of global change, but also very specifically to sediment. And that's because we do a lot to our river systems, but also to the landscape. So there's actually a conflicting sort of processes or drivers that we humans, our societies are doing. On one hand, we dam the rivers, right? We build dams on the rivers, which are very efficient in terms of trapping sediment, so preventing sediment from flowing through our river system. But we also, through land use, change the soil erosion energy and soil erosion rates, and therefore all of these processes may conflict with each other, which makes it even more difficult to understand and to model. But humans, especially in the last 200 years, have been a major driver of changes in sediment flux in rivers. So taking all of that and try to create models to predict that can be quite challenging, as you can imagine. Like any other field of environmental science, right? You're trying with numerical models, you're trying to represent a very complex system within some mathematical rules within a computer program. So as a result, there's been a lot of significant evolution of numerical modeling of fluvial sediment over the years. There's a large variety of concepts and scales of application. Traditionally, it's been linked to soil erosion estimation. That's been sort of the roots of fluvial sediment modeling can be linked to soil erosion modeling, because especially since the mid 20th century, so that you had the Dust Bowl in the US in the 1930s that brought a lot of attention to soil erosion in the US, and it was a big boost to trying to model soil erosion. And these days, or still, we are heavily relying on empirical relationship between observations and processes within the catchment and the river. The problem that we face with using empirical links is the fact that we don't have enough observation of sediment globally. The US is probably the richest location in terms of the extent of continental or near continental scale, with relatively a lot of monitoring of sediment, but that's is definitely not the case in a lot of other countries and a lot of other regions. There have been a lot of review papers that have been published over the years looking at soil erosion modeling and river modeling and fluvial sediment modeling, a lot less for fluvial sediment modeling actually. So this paper that I took this from is from Devante at 2013. And the reason why I put this here and kind of advertise this paper, I wasn't a co-author on it or anything like that, is because they, I think, were the first one, and I don't think there's been much since, to look at what they call regional soil yield or sediment yield models, sediment erosion and transport models. So they compare these models that you see here. Some of them are global in scale. Actually, I believe these four, oops, sorry. But among them is the WBM SED, which is my model that I'm going to talk a lot about. But we're also going to talk about the Bogart equation. I also would want to draw your attention to the Peltier at 2012 model, another good one. At the time, these two, the Peltier and WBM SED, were the only sort of global sediment, fluvial sediment transport models that's been around. Since then, there's been quite a revival of that topic, and I'm going to talk about it at the end of my presentation. So I need to take a move on. So the Bogart equation, or BQ-Art equation, was first fully published in 2017 by Savitsky and Milliman. And it's a really nice, I think this is the first global sediment flux model, and it predicts sort of long-term average sediment load at the outlet of a river as a function of discharge, which is over here, area, relief, temperature, sediment trapping behind reservoir, anthropogenic erosivity, lithology is a proxy for sediment production rate, and ice cover, because ice is also very important, as we heard. Now, following on the Savitsky and Milliman, so I was the lead, or still am the lead, on the development of the WBM SED model, which basically took the Bogart equation as the governing equation and express it in a spatially and temporally explicit global scale modeling framework. It was part of a larger hydrological framework that was developed at the time. And it includes both suspended and bed load. I'm going to talk a little bit about that. And it can also be applied regionally. It doesn't have to be global scale. So again, it used the Bogart equation as its governing equation, and then break it down using the Psi model into daily predictions. I would refer you to the 2013 paper we published. This was the first paper that kind of showed that concept behind this model. The model used or builds on an existing global hydrology model called WBM+, which is a really good model, not well enough known in my view, because the reason why it's good and kind of is different than others, it has all of these anthropogenic factors already built into this model. So we were very fortunate to be able to build our sediment component within this framework. So you have irrigation and recharge of groundwater, uptake of reservoir water, crops, all the different component, dam operation to affect reservoirs. So all that effect there, I'm gonna skip over that. And a lot of this was also explained in our 2014 paper. I'm going to skip that slide. I'm a little behind on where I want to be. So the model, I'm going to show you some application of this model. So just to give you a sense, we run this model at 6 arc-minute resolution, which is about 11 kilometers grid cells. It takes about less than an hour to simulate 1 year at the daily time frame. We use a high performance computer cluster, but you can run it on your on a strong desktop if you have it. You don't have to have a supercomputer. However, it does have a very significant input data set, and it generates very large output data sets. So you need a lot of disk space. So that's one of the advantages of using a high performance computer cluster. These are just some example of running it at much higher resolution regionally. So you see here the island of Oahu in Hawaii at 30-meter resolution. I simulated Australia at 15 arc-second, the part of the US, and so on. So you can apply it at much higher resolution regionally if you need to and want to. All right. Let's talk about some application. One of the big advantages of using models in general and global fluvial sediment model in particular is our ability to isolate different parameters and also look into the future, into the past, where we don't have observations. So I want to show you some example of that. I'm going to start with a study we did as part of a master thesis in my lab that looks at anthropogenic impact. We actually now have a PhD project that's moving way beyond what I'm going to present to you today. But I kind of mentioned before that humans have a conflicting effect on sediment, on fluvial sediment flux. On one hand, we're very efficient at trapping sediment behind dams, but we have also caused a lot of increase in erosion. So what is the net impact of that? There have been some estimates at the past that put the net impact as 30% reduction in global sediment flux to the ocean. That was for Voris-Marti estimate in 2003. There's also been an estimate for discharge, a decrease of 3.5 in water discharge to the ocean, again, on a global scale average because of human activity. So with our modeling capability, we can actually test these and create an exercise in which we can control this different aspect of the anthropogenic factors and therefore isolate them and see how they behave. So for example, in this case, we see, all right, what happens if we switched off or remove all the dams and also look at natural land use? So what is going to be the impact? So we compare that to what we call the disturb simulation, which is the most realistic one. And then what happened if we just look at the effect of land use? What happened if we just look at the impact of dams? So as you can see just from these maps, it's a very complex story, right? Different rivers behave in different ways. You can average that globally. And what we did in this, just to make it a little bit simpler, is to average that per continent. So we took different continents for it. So at the top table, you see, okay, what is the percent difference between the pristine and the trapping? So if we just put the reservoir, so if we remove the reservoirs or the dams, then you get a huge increase in sediment in Asia, more moderate one in North America and in Europe, and even more moderate in South America and Africa and Oceania, where you don't have as many reservoir. And then you can look at what is the net impact. And what's interesting is Asia here. And, you know, you should take this with a grain of salt. Obviously, there's a lot of complexities that are not represented. But Asia, even though the impact of dams is huge in trapping sediment, the net effect is very close to zero, because humans are also increasing the amount of erosion very actively because of population density and somewhat lack of soil conservation compared to other countries. But you can see, so for in Europe and in North America, you get quite a very significant decrease in the amount of sediment that flows to the oceans. Another example, which I really like, this was a couple of papers that were published very recently, the last couple of years, by Frances Dunn, who at the time was a PhD student at the University of Southampton in the UK. Now she's a postdoc at in the Netherlands. And what she did, she used the model, again, with a somewhat similar or more extensive scenarios of testing. And she looked at she looked at to the future, by the way, so the end of the 21st century, and she looked at different RCP. So these are the global climate change model, right? The general circulation models that are used to project the future climate. She looked at the 4 different scenarios, so business as usual, all the way to very effective reduction in greenhouse gases, and also 3 socioeconomic scenarios, so increase in population, development, and so on. And she made some predictions about, or through that, she was able to isolate and predict the future of sediment flux into large river deltas. And I'm not going to go into the whole, again, very complex story here. I would refer you to these 2 papers. I think they're really good papers if you're interested. And generally, just to give you the punchline, if you will, so we do see a mean and maximum decline of 38 and 83 respectively. So an average decline of 38% towards the end of the 21st century in terms of the amount of sediment that flows into these 47 deltas. And that's a big story. That's a big prediction, because the deltas are very sensitive to the amount of sediment, as we said, and a reduction in sediment flux into deltas is bad news to a lot of these deltas. And building off that, this is a PhD project in my lab by Danuk Monashinge. And he's looking now at the next step, which is what is the actual impact of reducing sediment flux on deltas. So he's using remote sensing to actually map and quantify changes in the river delta morphology. So in this picture here, you see one of the distributaries of the Nile River Delta. We talked about the Nile a little bit. And you see the lines here are the coastline going back to 1973 all the way to 2014. And you see that erosion on the delta, and that's because the Nile has seen a massive reduction in the amount of sediment since the establishment of the Aswan Dam. another very recent paper just published this year by my PhD student, Nishani Moragoda, and she was, what we did was isolate the climate signal. So we took an ensemble of 5 GCM, so these general circulation models, and all these 4 RCP, and we said, okay, if we just look at climate change towards the end of the 21st century, how is that going to impact discharge and sediment flux in global rivers? And again, the picture is quite complex, obviously, in different regions. Generally, we do see an increase, again, just because of climate change in sediment and discharge, which is not surprising because we do expect more precipitation in the future because of global warming and therefore more atmospheric moisture and so on. But we also found one of the takeaway from this study was that the differences between the scenarios are pretty significant, especially for discharge, but also for sediment. So this is the percent difference from the start of the 21st century or for the average then at the end, the last decade. So, you know, over 15% more sediment and 10% more discharge at a global scale. Actually, the averaging doesn't really tell a very compelling story in a way because the effect in different basins can be very, very dramatic. This study, I just want to show it in passing. First, because we haven't really published it beyond just an abstract, but also because I think this is a really cool study. And what we are doing here is isolating the impact of tropical cyclones on discharge and sediment. So this is a really cool application of this model, I think, because what we've done, this is my colleagues at the University of Southampton, we basically took the precipitation input that we have for the model, extract the precipitation that is associated with tropical cyclones using the tropical cyclone track data set, and then compare the sediment and discharge water discharge prediction between the 2 scenarios, right? The realistic and the one without the tropical cyclone. And then we can quantify the contribution of tropical cyclones to sediment flux. Now, again, the story, when you average it out, it doesn't look very dramatic about, about 2% contribution globally, but the effect on specific river systems can be very, very dramatic. We found that especially in Northern Australia, that's where we found very, very significant contribution. So again, trying to quantify the contribution of tropical cyclone, and that is a really nice exercise, but also is important to talk about the future and the impact of climate change, because we know, or the main hypothesis that or the notion that we now have, that global warming will increase the intensity of tropical cyclones. So by understanding how they actually affect global sediment flux, that's another piece of that puzzle. Another application, another paper that I would like to advertise, this was published in 2019. Jaya Savitsky was the lead author on this. This is, I think, a really, really important paper, because what it looked on was the contribution or the effect or the relevance of river temperature to fluvial sediment. And the reason why it's important is because river temperature, water temperature can change dramatically even within a river basin, but definitely globally, and also seasonally, it can change dramatically, especially for rivers that flow along latitudes from south to north, or from north to south, or from very high elevation to low elevation, which many rivers do as well. So here, for example, we see the temperature profile of the Mississippi River that change in terms of average temperature by over 10 degrees, 12 degrees C on average. This is the Lena here, which is less dramatic in terms of temperature change on average, but you can see some major jump, especially when you have tributaries coming in. And the reason why this is, I think, a really important study and very interesting is because water temperature has a major impact on water viscosity, density, and therefore, and settling velocity, and therefore the amount of sediment that the water can carry. So what we have found in this paper is that Well, first of all, it's known that these models, even high resolution models, they basically completely neglect temperature. And what we demonstrate in this paper that we shouldn't, because water temperature actually exert very significant impact on sediment flux, which is a parameter that we just ignored so far. I mentioned that we are we added a bed load component to the WBM SED model, and this is a paper I'm currently working on. For the sake of time, I'm actually going to move on just because this is, and I'm just going to mention the particulate nutrient component that we have for the model. We used what's called the global news model that was published in 2010. And it has a bunch of equations that we just plugged into the WBM SED model, and we can have a fairly robust prediction of particulate nutrient, organic carbon, and phosphorus. All right, so that was the sort of where we are or where we were with the WBM SED model. I want to finish this presentation by looking at some really exciting new developments. So as I mentioned earlier, there's been a renaissance in global fluvial sediment modeling in the last just couple of years. And a lot of it comes from the availability of data, but also I think much of it is driven by the Earth system models. So Earth system models are these models that's trying to, well, model the entire Earth system. So linking the atmosphere and the oceans and the landscape or the continents all together. And up till just, as I said, a couple of years ago, rivers were pretty much ignored. And now there's this renaissance and people try to do that. One of the leading authors is called Ji Tang, and he published this paper in 2018. I think it was his first paper about this. And this paper focused about, they were trying to identify the best model to use to plug into what's called the energy exascale Earth system model, E3SM. This is probably the best known Earth system model, especially in the US. It was developed and funded by the US Department of Energy. G10 has developed a sediment component. He found out that the Morgan equation or model actually was the best one. It's actually here. So he's been using it, plugging it into his model, and got really interesting results. Another really cool paper that was just published by a group from Japan, Hatono and Yoshimura, sorry, and they develop, again, a global sediment flux model that not only look at what's going on at the landscape of how much sediment is coming to the river system, they actually model the fate or the processes within the channel itself in terms of erosion and deposition of sediment within the channel, which I think was really interesting. And they got very good results as well. So another paper to be aware of. And again, all of these things are coming now up front. It was pretty lonely, I can tell you, for a long time when it comes to global sediment model. Another two examples that are exciting and new. So Baroli et al. Published this global soil erosion paper, soil erosion model based on the RUSLE equation. And it was a static model to my understanding, at least initially, but it was very high resolution, 250 meter resolution. And so they provide basically soil erosion at the landscape, and that allow people like Grill et al. That published a paper last year in Nature called Mapping the World Free-Flowing Rivers to try to use that to flow that soil erosion into the river system and understand or try to create an index of how pristine are all the rivers around the world. Another paper really worth getting to know. So, yeah, I'm really good on time, I see. So this is pretty much my last slide. And I want to talk about the future very quickly, at least the way I see it. And obviously different people have different prospects. So with all this exciting new development that's been coming online just in the last couple of years, what we are working on, and I think this is other people are working on as well, is to move from maybe more toward physically based understanding, or at least more explicit modeling of sediment transport within the river system. So empiricism is good, but it has a lot of limitation. And we need to start linking more explicitly within these global models, the landscape processing. So again, we heard about gullying, but soil erosion in general, landslides, and all these other factors that affect sediment dynamics within the basin. So the time is now right to put all of these together within a model. It was not very feasible just up till now. But there's still a lot of work to be done. So linking all of these small scale hill slope and fluvial processes into a basin scale understanding of sediment dynamic. One of the big things that we need to work on is really do a good job at linking or understanding the interconnectivity between climate and anthropogenic modification of the landscape. So I showed you that paper that we published about isolating climate change. I also showed you a paper about looking at, or a couple of papers looking at anthropogenic effect. However, everything is connected, right? So climate affects how human behaves and how they modify the landscape and how they interact with the landscape and damming and everything. So everything is connected, which makes it difficult. But this is, if we want to understand the future, I think we need to go beyond just plugging in those things individually and try to find the interconnectivity. Extreme hydrological events, as I said, are very difficult to model, and especially their effect of sediment, because observations are really sparse. However, we know that floods, especially in many river systems, are very, very significant control on sediment dynamics. So this is a very much a future direction that needs to be taken. And then I want to finish that with looking at nutrients and carbon. I call it the so what kind of result. So, all right, we all are sort of embedded within the sediment part of the story, but really sediment in itself is interesting, but what are the impact, which is how I started, so it kind of closing the loop on my talk. Nutrients and carbon are things that affect ecosystem, atmospheric systems, and so on. So we need to link everything together within this modeling system. And again, these Earth system models are a good way to do that. So, smack on time. If you have any more questions, feel free to email me, obviously now, but I'm very happy to answer your emails. Also, you can check out some of my publications on my website. And that's it. That's what I had.
Thank you, Sagy, for such a really global talk. That's such a planetary point of view. And we have a couple of questions. And the first question is from Pankaj Kumar. The question is, why intermixing, even after dozens of kilometers, doesn't happen between the streams? There must be enough turbulence.
Well, it's because, to my understanding, okay, I should put some caveat, I didn't study it myself, but for my understanding, a lot of it has to do with the water density that's so different. The temperature between the two streams is very significantly different. And I believe the Rio Negro, well, you know what, I don't want to say which is which, but I think that's the main story. So it just takes a while. You have this sort of barrier there that takes a while to mix. And it's not unique to the Rio Negro. You see that a lot in river confluences, but it's just such an extreme example because one river is so heavy on sediment load and so it's so poor or so little sediment load, and it's obviously two very large rivers.
Yeah, thank you very much. In Russia, we have one more great example of confluencing rivers with different density. This is the confluence of the Volga and the Oka. The Volga is dammed and the Oka is a free-flowing river, and they do not mix, I think, more than 200 kilometers. They flow, yeah, separately. It's great. It's really great, amazing natural event. So one more question is, yeah, mine from me. It's very interesting and a bit, it's really worrying how rivers lose their deltas, because there are a lot of people live, especially in Asia, yeah, in deltas. So people lose their homes. But as I know, there are few examples of recovering deltas, restoration deltas after dams removal. How do you think? What are the real, I don't know, some measures, maybe some, I don't know, real different, I don't know, construction measures to recover the sediment fluxes and not to remove dams. I mean, or maybe just change management regime or something. I think it's possible to study using models or I don't know.
Yeah, so yeah, you're right. Well, first of all, I didn't go into that at all, but deltas are extremely complex systems. So
Yeah.
there's a lot going on. You're absolutely right. Extremely important. Hundreds of millions of people live in deltas. Deltas are kind of bread baskets for a lot of communities in a lot of countries, because they can be extremely productive in terms of agriculture because of all the sediment and nutrients that come into them. There's also a lot of subsidence that happens in river deltas because of groundwater uptake and buildings and compaction of deltas. And if you couple that with the erosion of deltas because of lack of sediment, one of the inverse impact is increased susceptibility to flooding in river deltas, because you basically you lower the delta by different processes. You starve it of sediment, there's compaction, as I said, and so on, and sea level is rising. So everything together is a big concern for people living in deltas. Now, in terms of recovering deltas, there's a lot of things that have been done all over the world. One is trying to sort of armor the delta, right? So you put protection to try to reduce the erosion of the delta channels or coast. So you actively you put levees or whatever it is to try to shield the delta from erosion. And that's been happening all over the world. One of the best examples when you talk about trying to recover a delta is the Mississippi Delta, because the Mississippi, not surprising, because of all the engineering that's been going on for, over 100 years, in the Mississippi, dams and armoring and levees and so on, the Mississippi Delta has seen a major decrease in sediment flux, and as a result, a lot of erosion, mainly, excuse me, mainly, not mainly, but most notably wetland. So wetlands have been decimated, still are. It's not by any means solved. Still are decimated in the Mississippi Delta because wetlands require that annual influx of sediment through especially flooding. So what they've been doing in the Mississippi, they kind of breach some of the levees and the channeling within the Mississippi Delta to allow sediment to move out, and not because the Mississippi Delta is also, I have a picture of it somewhere over here, is also extremely elongated. So where's my Mississippi? No. Never mind. I'm trying to look at my slides while I'm talking to you. So the Mississippi is also very elongated, so the water leaves the delta quite far away from the coast. from the river itself. So they breach that. So that's one way to try to do it. But in reality, if you don't have the sediment because it's trapped somewhere upstream, it's really hard to recover that. Although I should say that we are now working on a new project. I didn't show any of that. And Sergey, that should be particularly interesting to you, I think. Looking at remote sensing by a colleague in the US of sediment, and we're trying to get a better sense of how sediment is really trapped behind dams and how much is it. Because we have all these sediment trapping estimates, but we know they're not very good because there's not a lot of data out there. So with remote sensing, you can actually really quantify the amount of sediment that's being trapped. And so that's something that I think is quite exciting. But yeah, I mean, I think there's, because this is one of those, like climate change is this slow moving disaster,
Right.
we don't necessarily do much about it in many cases. We try to solve it with patching it, but a lot of time engineering solutions like armoring the coastline and so on, they can come back and bite you because sometimes they have negative effect in the long run. That's been the case in many locations. So I understand, the Brahmaputra, for example, where you have a lot of flooding there. There's been a lot of effort now to try to protect the communities along the Brahmaputra in Bangladesh. So they're now building all these levees and armoring the river, which is a very wild river. What are the long-term impact of that? We see that in New Orleans, for example, in the Mississippi, they build these levees to protect cities in the lower Mississippi River. As a result, the rivers keep rising because of you need to build, increase the size of the levees, but the cities are getting lower and lower relative to these. And you see it all over the world, right? This is not unique to New Orleans. New Orleans is just an extreme example because it's a big city that's basically below sea level. And therefore, every time there's a big event, it's at a risk of basically being completely flooded. So anyway, I kind of went off a little further than what you asked, but deltas are really, really
interesting. Yeah, I completely agree with you. And maybe sometimes it's better to looking at natural-based solutions. However, I don't know any of them. Yeah, but and we have one more question from Pankaj Kumar. Question is how to model or include gulling in global erosion scale. Is there any model for regional scale which count for sheet as well as gully erosion?
So really good question. It's going to be hard, in my view, to really, explicitly model gullying per se. The solution, I think, is to find proxies to gullying potential and gullying severity, and that's include all the other things like sheet erosion and so on. I can tell you, so these models that I presented, those recent models that were just published, and this was not my models. I'm just aware of them. I didn't develop them. What they did, they either use what's called the RUSLE or USLE style equations, as I showed one of them explicitly doing that. And what it says is, it's basically giving you some sort of a proxy of how erosive is a landscape based on its soil characteristics, its topography, precipitation characteristics, land cover, and so on. So that's basically what these are doing in a nutshell. Now, going even more explicitly than that, meaning looking at something like landform evolution models that explicitly simulate the gullying or surface erosion, and then trying to couple that maybe in the future that will be possible. The problem is right now is these models require very high resolution implementation, which is not feasible at very large scales. We also don't have the data really at that scales. So these are the current limitation, but I'm sure there's a lot of young people that are listening. So your career is in front of you. So yeah, this is where we are going. I like to think of the climate community. So they develop what we now use, right? Weather predictions and forecasting. And they use global climate models that we use to project future climate. Over the years, they have built on their improvements to look at more higher and higher scale or higher and higher resolution and solving more and more of the dynamics. And they also started a lot of for example, weather forecasting. It still is, to be honest, but it was definitely initially a lot of statistics, right? They said, okay, yesterday was like this, or 5 days ago were like this. Most likely with everything we see, this is what the next 2 days are gonna look like. It's still some of that, but now they are able to really simulate a lot of the energy and processes in clouds. And anyway, I think this is where the geomorphology community is also moving towards. So we always lag in a little bit just because our topic is is much less funded, and there's much less critical mass when it comes to, you know, sediment modeling compared to weather or even water modeling, hydrology. So, but to answer the question, yeah, at the moment, I don't see us explicitly simulating these processes at that scale, but this is where we sort of need to move to one way or the other.
Thank you, Sagy. I think it's a good finishing point, you know, to know how to move forward and which topic is the most interesting in this area. So I think we're finished. It was the last lecture for today. I hope you're so you haven't tired yet. Lecturers as well as participants, lecturers. And I don't know, I think we're finishing for today, Sergey, right? Would you like to do some announcement or for tomorrow meeting?
No, I would say thanks also for speakers today and for the last lecturer, Sagy. Thank you a lot you joined and accepted our invitation. That's really a good silver line, as you said, during these times that we have these opportunities to bring people together. We would never imagine even such kind of possibilities to invite so many excellent lecturers to the such kind of seminar, that we will be able to, that everyone is coming, so that's, yeah, something good is happening in the world. Yeah. Thank you.
Thank you. Yeah, thank you very much.
And we'll keep in touch. So we are finishing now the YouTube, and tomorrow at 4 Moscow time we have 4 more lectures and the end of this lecture seminar series. So, and please participants join tomorrow our lectures. You have the schedule on the website and in the